Hi and welcome to a lesson of real analysis, and today we are going to discuss some more topics on real analysis. So we were uh, doing the chapter of sequences, and we talk about the convergent sequences, and we take some examples and some theorems on convergent sequences. Now there are some more principles by which we can show that a sequence is convergent. So let's talk about the first squeeze principle that says if AN, BN, and CN are sequences such that AN approaches the limit L, that is, it converges to the limit L, and CN, another sequence that also converges to the limit L, and for all n belongs to n natural numbers, this is the condition that the sequence Bn, for which we have to show that it is convergent if it's greater than or equals to An and less than or equals to Cn. So actually it's bounded between two sequences, that is An and Cn. Then we can say that Bn also converges to the limit L. So now let's start the proof that if this condition is true. So suppose that there are three sequences, namely AN, BN, and CN, and they are convergent sequences such that AN converges to L as given in the theorem, CN converges to L, and for all n belongs to naturals, this condition is satisfied. That is, Bn is bounded between the two sequences. And now assume that epsilon is greater than 0. So by definition, we are going to prove this thing now. So by definition, we know that if AN converges to L, then this mod of AN minus L is less than epsilon. So this is the definition of the limit. Sorry, convergence of sequence, right? And again, Cn converges to L implies that Cn minus L is also less than epsilon. So we can exploit these two conditions. So since we can remove the mod and we can write AN minus L is bounded between negative epsilon and positive epsilon. Similarly for Cn, we can write that this is bounded between negative epsilon and positive epsilon, right? So again, if we add L on all three sides, so L minus epsilon is less than An is less than L plus epsilon here. Similarly for Cn, we can do the same thing. Therefore, now An is greater than L minus epsilon. From here, we can see that An is greater than L minus epsilon. And again, An is less than Cn, because here we are taking that Bn is greater than or equals to An, and Bn is less than or equals to Cn. Therefore, this An is less than Cn. And so if An is less than Cn, then we have here Cn is less than L plus epsilon. So we can take these these two conditions, this one and this one, and then we can write that this Cn is greater than An and it's less than L plus epsilon. So we can write that An is greater than L minus epsilon, where An is less than equals to Bn given in the condition, and Bn is less than equals to Cn, and therefore Cn is less than L plus epsilon. And if we remove these two elements, An and Cn, therefore Bn is greater than L minus epsilon and Bn is lesser than L plus epsilon. Because we are saying that Bn is less than or equals to Cn, but Cn is strictly less than L plus epsilon. So Bn is also strictly less than L plus epsilon. And here also the same argument, because Bn is greater than or equals to An and An is strictly greater than L minus epsilon. This implies that Bn is greater than L minus epsilon, which implies that Bn is bounded between L plus epsilon and L minus epsilon. Again, if we add subtract L from all sides, so we'll get minus epsilon less than Bn minus L less than epsilon, which implies that the mod of Bn minus L is less than epsilon. This thing implies this thing here, right? So this is by definition, this is proof that Bn converges to L. So that's the first squeeze principle, that if we are given with a sequence and we can show that the sequence is bounded between two convergent sequences whose limit is approaching to L, then the sequence that we are considering for the convergence also converges to L. So we'll take some examples in couple of minutes after some theorems, and we'll see how this works. So now we have the second squeeze principle, which says that if an and bn are two sequences, they're such that bn converges to 0, that this sequence bn converges to 0, and there exists n naught belongs to the natural such that n is greater than equals to n naught, implies that an minus l is less than equals to bn. Now this thing here is important, that an minus L is less than equals to Bn, and Bn is a convergent sequence, such convergence that it's we can say it's a null sequence whose converges to 0, whose limit is 0, so it is a null sequence. Then An also converges to its limit L here. All right, so let's see how this works. Okay, now suppose that A and B are convergent sequences, then by definition and the given conditions, we have Bn is converging to 0, which implies that Bn minus 0 is less than epsilon. If we remove the mod, we can get negative epsilon less than Bn, and Bn is less than epsilon. And now from this condition that is given, An minus L is less than equals to Bn, implies that Bn, okay, this implies that this An minus L is less than equals to Bn, greater than equals to negative Bn. All right, and then we have the condition that Bn is less than epsilon, so we can replace this Bn with epsilon, because from here we can see that Bn is less than epsilon. And so if we remove this Bn and replace with this epsilon, so we can see that An minus L is less than epsilon, which implies by definition that An minus L is bounded between negative and positive epsilon. All right, so An is bounded between negative and n minus L, sorry, is bounded between negative and positive epsilon. And if we add L on all sides, we get this thing here, that is L plus. An is bounded between L minus epsilon and L plus epsilon. So hence, by the definition of the limit, An converges to L. So this is the proof of the theorem, that is the second squeeze principle. Okay, now let's do a problem that use the second squeeze principle to prove that this converges to this. Okay, so we have in the second squeeze principle that if Bn is a sequence that converges to 0 and An minus L is less than equal Bn, then it implies that An converges to L. All right, so this is the second squeeze principle that we are need to keep in mind. And then by definition of the limits, we know that if this converges to this, then this thing here is mod of this thing is less than epsilon. We know that by definition of the limits, that should be less than epsilon. So now let's start solving this. So we take LCM on LCM here. Okay, so it's 3 times 2n plus 3 minus 2 times 3n minus 2, or 9n minus 21. And then some cancellations, and we have 9 plus 14, that is 23 over 9 minus 21. Now this thing here is in the mod, so it's a positive number, so we can remove the modulus. But here there is a problem that it can be negative and positive as well, because n varies from 1 to 3 and so on. And if we put n equals 1 here or n equals 2 here, this mod is going to be negative. So if we want to remove the mod, then we should consider n greater than or equals to 3, because we don't want this mod to be negative, right? So we are keeping it strictly positive. Therefore, we have to consider n greater than or equals to 3. We cannot consider n equals to 1 and n equals to 2. So now we can write that this implies 23 over 9 and minus 1 is this mod is removed now, this mod, because we are saying that now for all n greater than or equals to 3, right? So now we can remove the mod because now it's strictly positive, and we can see that now this sequence, this one here, is say that this sequence here, say we are saying that this sequence, given sequence is an, let's say. Now we have to find a sequence Bn which is converging to 0, and it's the sequence an minus L is less than that sequence Bn. Okay, so we can now say that this thing here, 23 over n 9 and minus 21, is less than 23 over 9 and minus n when n is greater than or equals to 22. Okay, we can check that if n is greater than or equals to 22, this thing becomes greater, right, from this thing, and we can put in the value of n, 22 or some greater values than 22, and we can check whether it's fine or not. So now this, we have found this Bn that is greater than this An, and we will show that now this Bn converges to 0, then this will imply that the sequence An converges to its given limit that is given in the question, that is 2 over 3. So now this sequence Bn is greater than this sequence, so we can write 23 over 8n. So it's 23 over 8n, so it's less than 24 over 8n. It's fine, we can write that. So 8 1s 8, 8 3s are 24, so it is equals to 3 over n, and we know that this sequence 3 over n will converge to 0. We already have proved this thing in the previous classes, that the limit, the 1 over n approaches to 0. So limit 2 over n, 3 over n approaches to 0, right? So this thing approaches to 0, so this was our Bn, and then therefore this sequence 3 over n is greater than the given sequence here, that B minus L. This was our sequence B minus L. Keep in mind that, sorry, A minus L, not B minus L. It was A, and we subtracted An minus L. So this was our, and we simplified this sequence. So this sequence here is our An minus L. Therefore, we can write that 23 over 9 and minus 21 is less than 3 over n. Therefore, this sequence 3 over n converging to 0 implies that this An converges to its limit L, which is given in the question. So this is proof that this sequence is converging to its limit L by the second squeeze principle. Now let's take one more example, that is limit n tends to infinity, 3n squared minus 4n over n squared plus 5 equals 3. Now we can again apply the definition of the limit and simplify the problem. So up till here, we have simplified the problem, but it's negative 4n minus 15. So if it's negative 4n and minus 15, so both are negative. So if we want to remove the mod, we can remove the mod because both of them will be positive. It's a mod, so we can remove the mod, keeping both of them positive. And n squared plus 5 is already positive, so no worries with this element here. Now we can show that this is less than 4n plus n over n squared for n squared plus 5 for all n greater than or equals to 15. So when n is greater than or equals to 15, this thing here is going to be greater than this thing here. So this is our sequence An minus L, and this is now our sequence Bn, and we have to show that this Bn converges to 0, so it will imply that this an converges to its limit L. So now this is 4n plus 5 and 5n, and since now this 5n over n squared plus 5 is less than this 5n over n squared, obviously, because we are removing this 5. All right, so we are removing this 5, therefore this will be strictly greater because the denominator will be lesser, so it will be overall it will be greater number than this number here on the left side. So now it n and n cancels, we get 5 over n. I mean, we know that limit n tends infinity, this thing goes to 0. So if this goes to 0, we said that this thing 4n plus 15 over n squared plus 5 is less than 5 over n, and this goes to 0, it implies that this an minus L, that is less than equals to Bn, also converges to its limit. An is converging to its limit L. So now it's fine that this is converging to the limit, so it's proved, right? And this problem we already discussed in the previous video lecture, that this sequence n square root n nth root of number n is converging to 1. All right, so again we take an equals this thing n square root of n minus 1. We call it a sequence an equals to this thing, then this is equals to an plus 1, and if we apply 1 over okay, if we apply the nth root on both sides, n on both sides in the power, so we get n equals to this thing here. We apply the binomial theorem and we take some terms. So here are the terms of the binomial theorem, and if we neglect these terms, because this thing n is equals to this whole stuff, but if we neglect some of the terms, few of the terms here, then eventually this is going to be greater than this. For instance, if we have 3 plus 1 and we have 4 equals to 3 plus 1, if I remove this one, then eventually 4 is going to be greater than equals to 3. We can write like that because there are infinite terms in the sequence, right? So but not here, we cannot write that this is equals is greater than 3, right? But here in finite terms, so we can write this that is greater than equals to this thing here. Then again, if I remove these two elements more, now I can say that it's strictly greater than this thing here. And by some algebraic manipulation, here is 2 factorial is on the left side. This n cancels with this n, then we have 2 is greater than n minus 1, an squared. Then take n in minus 1 to the left in the denominator, then it's greater than an squared. Since an is squared, it's squared, so it's all time it's positive because it's a square on an, so every element is positive, therefore an square is greater than equals to 0. It cannot be less than 0 because of this square, and this is less than this thing here, we already have shown. So again, we know that this sequence limit n tends to infinity, this sequence converges to 0, so therefore the sequence an is also convergent, right? So this sequence that we considered an equals to n square root of n minus 1 is it's convergent, therefore this is this one is the limit of this sequence. Okay, now we have one more problem, that for all c greater than 0, c is a real number, limit n tends to infinity, nth root of c equals 1. We can divide this problem into 3 parts, taking case 1, 2, 3 when c is greater than 1, when c is equals to 1, and when c is between 0 and 1. So when c is greater than 1, we have n square root n greater than n square root c. This we already have proved that this converges to 1. This is proved now in the above example, so it's proved. And we know that this thing here is greater than this thing, and this converges to 1. Therefore, this is bounded now. N square root of c is bounded between 1 and it's less than this thing, because this thing cannot be greater than 1. Uh, so this is bounded between 1 and n square root of n. Therefore, this converges to 1, implies that this thing n square root of c is also converging to 1. Okay, and then if c equals to 1, this is a trivial case that 1 power 1 over infinity is 1 over 1 power 0, and 1 power 0 is 1, so it's a trivial case. Again, for case 3, if c is bounded between 0 and 1, then we can say that 1 over c is greater than 1. So if 1 over c is greater than 1, we can apply a square root uh, n to square root on 1 over c, and also n to square root on 1. So, and apply the limits on both sides. So this thing will become, this thing here will become this 1 over n, limit n tends to infinity, 1 over n square root of c, and n square root of c we already have proved here that it's converging to 1. Here we have proved that this is converging to 1, so it's 1 over n square root of c, so it's converging to 1, therefore it's 1 over 1, that is going to 1. So this is converging to 1 for c bounded between 0 and 1. Now we have one more problem, that limit n squared over 2n converges or diverges. So we have to check whether it converges or not. Simply now we can squeeze this thing. We know that this is less than, we can say 1.9 power n over 2 power n for all n greater than equals to 6. Okay, we can check it by calculator that this thing is less than this here for all n greater than equals to 6. Therefore 1.9 over 2 power n, this thing here, we can say that it's 1.9 over 2 power n. Since this thing is bounded between 0 and 1, and we have shown above that if we have some r, that is mod of r is less than 1, then r power n converges to 0. Okay, so now this thing here is bounded between 0 and 1. So I forgot to write this thing n tend to infinity. So this thing here, limit n tend to infinity a over b, if you call it c, so the power n, when a is less than b, it goes to 0. So this limit goes to 0, which shows that this limit also goes to 0 because this is converging to 0. So bn converges to 0, implies that an also converges to 0 because an is less than bn in the case we have shown. Okay, so we have found a bn that is greater than an and it's converging to 0, implies that this series is also convergent and it's converging to 0. Now for this question, that is limit n tends to infinity c power n over n factorial, where c is positive real number. Now by ratio test, we can say that c power n plus 1. So what ratio test says that is, if we have for instance, if n squared plus 1, we have a sequence like this over n, then what we have to do is we have to test this sequence. Say this is n equals this thing, then we have to write a sequence an plus 1, that will be n plus 1 times n plus 1 is squared plus 1 over n plus 1. Okay, so okay, let's take it as n half, for instance, or we can say that it's n power 5/2. So it's n plus 1 power 5/2 like this. And if we divide this thing n plus 1 over n with the limit n tends to infinity, and we get the mod of this sequence less than 1, then we say that the sequence is convergent. So we are given with a sequence an here. So an in this case is cn over n factorial. So an plus 1 is going to be c power n plus 1 over n plus 1 factorial. Okay, now we are going to apply the ratio test. So it's cn plus 1, that is, we are going to do an plus 1 over an. Therefore, cn plus 1 over n plus 1 factorial divided by this thing. So we can write multiply by this in this way, okay, by simple mathematics. So now we can do some cancellation. We can split this c power n plus 1 into c power n dot c. So c power n cancels. And then we can write this n plus 1 factorial like this, n plus 1 factorial like this, n plus 1 times n factorial. So this n factorial cancels. We get c over n plus 1. And we know that this sequence goes to 0. Therefore, we can say that, and this is less than 1. So the limit L is less than 1. Therefore, now we can say that, okay, we have to apply the mod also. Keep in mind, it's important. So this mod of the sequence goes to 0, and 0 is less than 1. Therefore, the original sequence converges to 0. So note, if an is a sequence such that an is not equals to 0, such that limit n tends to infinity an plus 1 over n equals to some number L, and L is less than 1. This condition is important. And L is less than 1. So then limit n tends to infinity an equals 0. So this is the theorem for the ratio test, right? So these are some problems. Hope you guys will understand the lesson, and we'll come up with more problems and more theorems in the coming lessons. Thanks for watching the lesson. That's all for the time being. Goodbye.